So the next topic we will look at is reversible reactions and equilibria. And here we have an example of a reversible reaction as it goes through its different reactions. So these are the learning objectives. You're going to have to know that some reactions are reversible and how we indicate that. Describe some reversible reactions. I'm going to give you two examples, which are copper sulfate and ammonium chloride. Know that a reversible reaction can reach dynamic equilibrium, so we're going to find out what dynamic equilibrium is. Know that the characteristics of a reaction when they are dynamic, and again we'll go through that in detail. Understand why a catalyst doesn't affect the position of an equilibrium in the reversible reaction, and know the effect of changing either temperature or pressure on the position of equilibrium in a reversible reaction. And we're just going to look at a particular example to illustrate that.
In this lesson, we will learn about reversible reactions. When we fry an egg, it is impossible to unfry it. A lot of reactions work in the same way. Once it is done, it is irreversible. A good example is the combustion of magnesium to form magnesium oxide. Reversible reactions are reactions where formed products can revert or go back to their original reactants. Since the reaction can proceed in either direction, we use this reaction arrow to represent reversibility. An example of a reversible reaction is the thermal decomposition of ammonium chloride to form ammonia and hydrogen chloride. Place ammonium chloride in a boiling tube and heat using a Bunsen burner. Ensure that this is conducted in a fume cupboard, as ammonia and hydrogen chloride are both corrosive gases. If we hold red litmus paper at the mouth of the boiling tube, it turns blue, which confirms the presence of ammonia. Blue litmus paper turns red, which confirms the presence of hydrogen chloride. Remove the boiling tube from the heat and let cool. Have a look near the mouth of the boiling tube. You will see that there are white crystals. These are ammonium chloride crystals. So what has happened here? Ammonium chloride has thermally decomposed to ammonia and hydrogen chloride. The formed ammonia and hydrogen chloride have reacted to produce ammonium chloride. Therefore, this is a reversible reaction. Why is the thermal decomposition of ammonium chloride sometimes incorrectly called a sublimation reaction? Please pause the lesson to think about this, and resume when you are done. Here is a hint. Think about phase changes and what happens to a substance during a phase change. When a substance goes from the solid phase to a gas phase, it is said that it has sublimed. This phase change is not a reaction, as the substance itself has not changed. In our example, solid ammonium chloride did not form a gaseous ammonium chloride, but rather it decomposed under heat to form ammonia and hydrogen chloride. Therefore, it is not a sublimation reaction.
Okay, so from the video you would have now grasped an idea of what a reversible reaction is. Okay, so some chemical reactions are reversible. They can go either in the forward or back direction. And here's an example here, A plus B going to C plus D, but you'll notice that it has this interesting arrow this way, okay, which means that not only can it go from A to B to give C plus D, but it can go back again from C to D to A plus B. It is reversible. Okay, there's an example there, which you have to know, ammonium chloride. So if you heat ammonium chloride, it goes to form ammonia and hydrogen chloride, and then as it cools down, it reforms ammonium chloride. The reaction is indeed reversible. So if a reaction is exothermic in one direction, what must it be in the opposite direction? It must, of course, be endothermic. And we're now going to illustrate that by the second example you have to know, the heating of copper sulfate. So hydrated copper sulfate, so copper sulfate with water added, is blue. If you heat it, it becomes white. Okay, but if you add the water again, it goes from being white anhydrous copper sulfate and goes back to being hydrated copper sulfate, and it also releases heat. Okay, it's an exothermic process. So it's endothermic in the forward direction, is what we'd say, and exothermic in the backward direction. That's the symbol equation there. Okay, so you have to know both of those examples, the example of ammonium chloride and the example of hydrated copper sulfate, as both reversible example reactions.
In this lesson, you will learn about dynamic equilibrium, the conditions required for dynamic equilibrium to be reached, and examples of systems at equilibrium. Imagine you are digging a hole. You got it? Imagine, as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend, the hole gets larger. If your friend is filling the hole faster than you, the hole gets smaller. But if the two of you are working at the same speed, there would be no change to the size of the hole. The same concept can be applied to a reversible reaction. If the rate of the forward reaction, reactants to products, is the same as the reverse reaction, products to reactants, the reaction is said to be at equilibrium. This is called a dynamic equilibrium because both processes are occurring simultaneously, even though there is no overall observable change. For a chemical system, such as a reaction or a phase change, to be at equilibrium, it must meet two important criteria. First, it must be a reversible process. Second, it must be taking place in a closed system. A closed system is one where there is no exchange of matter, only exchange of energy. An example of a reaction at equilibrium is the reaction of hydrogen and iodine in a closed container to produce hydrogen iodide. At the start of the reaction, there is a high concentration of hydrogen and iodine, and the concentrations decrease as hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed, the reverse reaction is then able to occur. Over time, the concentrations of hydrogen, iodine, and hydrogen iodide remain constant. So what is happening here? The reaction of hydrogen and iodine to produce hydrogen iodide is occurring at the same rate as the decomposition of hydrogen iodide to hydrogen and iodine. So there are no observable changes, although both the forward and reverse reactions are occurring. This reaction has not stopped, but rather has reached dynamic equilibrium. What would happen to this reaction if the lid on top of the glass jar was opened? Please pause the lesson to think about this and resume when you are done. If the lid was removed, the system is no longer at equilibrium as the reactants and products, or matter, would be able to escape the system. Liquid bromine equilibrates to form gaseous bromine at room temperature. Remember that this is not a reaction, but rather a phase change. Phase changes can also reach equilibrium under the correct conditions. As liquid bromine evaporates, gaseous bromine condenses. Since these two processes are occurring simultaneously at the same rate, there is no observable macroscopic change, but the system is in fact in dynamic equilibrium. In summary, a chemical system is said to be at equilibrium when the rate of the forward reaction is the same as the rate of the reverse reaction. There are no observable changes, but both directions of the reaction are occurring, so it is a dynamic equilibrium.
So on the video in the last slide, you would have looked at reversible reactions. And when a reversible reaction occurs in a closed system, And when I mean a closed system, it means where there's no reactants being put into the system or no products are being taken away from the system. Okay, and the example would be in a sealed container, we have something called dynamic equilibrium. And dynamic equilibrium is when the reaction goes at the same rate in both the forward and back reactions. Okay, and it also means that the concentrations, say of this particular reaction here, of A, B, C, and D stay the same once dynamic equilibrium is met. Okay, now you can move the position of the equilibrium to favor either reactants or products, and that depends if the reaction is an endothermic or exothermic reaction. So in the case of endothermic reactions where you're actually giving heat in, okay, if you increase the temperature, you're going to increase the amount of products, which is illustrated by this animation here. As you can see, the amount of C and D is increasing. Okay, you get more products. If you lower the temperature of an endothermic reaction, then you're going to favor the reactants. Okay, you're going to move the equilibrium to the left. Okay, you're going to favor more less products. Okay, that's the case for endothermic reactions. In exothermic reactions, if you increase the temperature, the opposite is true. You end up forming less products if you increase the temperature. Okay, and also if you decrease the temperature, the opposite of the endothermic, you get more products. Okay, so in an exothermic reaction, if you lower the temperature, so if you're, say, combusting methane and you lower the temperature of the room, then you're going to end up forming more products. And this is a quick summary. So an increase in temperature moves to the right in endothermic, so you favor more products. And if you move to the left, if it's exothermic, okay, it favors the reactants. If you add a catalyst, there's no change, okay, and we're going to look at the reasons why as we move down. Okay, if you add a reactant, it moves to the right. Okay, if you remove a product, it moves to the right. And if you increase pressure, it moves to the side with the least number of molecules. And we're going to look at an example of that very soon. Now, why does adding a catalyst affect no change? Well, remember, of course, it's an equilibrium. Okay, so if you're adding a catalyst, you increase the rate of reaction of the forward reaction. Okay, that goes up, but you're also increasing the rate of reaction of the backward reaction. So if you're increasing the rate of the forward and the back reaction at the same rate, then it's not going to change the position of the equilibrium. So to illustrate these points around dynamic equilibrium, now let's look at making ammonia. Okay, so this guy is Fritz Haber. Guten Tag, my name is Fritz Haber, and I won the Nobel Prize for Chemistry. Yeah, I'm going to tell you how to use a reversible reaction to produce ammonia, a very important chemical. This is called the Haber process. Yeah, named after me. So in the Haber process, nitrogen plus hydrogen gives ammonia, but it's an equilibrium. So not only does nitrogen and hydrogen give ammonia, but ammonia can decompose back into nitrogen and hydrogen. Okay, and that's the simple equation there. So to produce ammonia from nitrogen and hydrogen, you have to use three conditions. Yeah. Okay. So for the formation of ammonia from the Born-Haber process, you have to use high pressure, you have to use a high temperature, and you have to use an ion catalyst. Okay, and a mixture of ammonia, hydrogen, and nitrogen is formed, but this is cooled, causing the ammonia to liquefy, and because of that, you're basically again pushing it to the right because you're removing a product. And the hydrogen and nitrogen gases are then recycled back into the system to be used again. Okay, so it's again increasing, I guess, the concentration of the nitrogen and hydrogen on the left hand of the equation, again pushing the reaction to the right, forming ammonia. So on the next slide, we're going to look at the different considerations that are required to consider the economics of the Born-Haber process and why these particular three conditions are used based on both economics and on the chemistry. Okay, so let's now look at the economics of the Haber process and why you have these particular conditions. Now remember, if it's an endothermic process, you increase the temperature, you get more products. And if it's an exothermic process, then you increase the temperature, you get increased reactants, which is kind of not what we want. Okay, so looking at this particular reaction of nitrogen plus hydrogen giving ammonia, you might think that it's actually an endothermic process, because remember, one of the process parameters is 450 degrees Celsius, which is pretty hot. Okay, however, that's not the case. The backward reaction of ammonia going to nitrogen and hydrogen is actually endothermic, whereas the forward reaction to make ammonia is actually exothermic. So why do they do it at 450 degrees Celsius? Well, if the temperature was decreased, okay, the amount of ammonia formed would, of course, increase. That makes sense, which is actually opposite of what we want. However, if the temperature is increased, which is what we see, the rate of reaction in both directions would increase, causing the ammonia to actually form faster. So it's a bit of a balance between those two concepts. So if the pressure was increased, which we do see, the amount of ammonia formed would increase because there are less molecules on the right-hand side of the equation. Okay. Okay, so in summary, at low temperatures, this would increase the yield of ammonia. Okay, so that's what we want. We want to get as much ammonia as possible, but the reaction is far too slow. It takes forever for this to happen, so you don't do that. However, at the high temperatures, this improves the speed of which ammonia is formed, but you don't get much ammonia formed. Okay, it forms quickly, but that's pretty much stops. At high pressure, this increases the yield of ammonia. The high pressure increases the yield of ammonia, but this is quite expensive. Okay, so that's the kind of cost that you have. So this is the reason why you use 200 atmospheres of pressure at 450 degrees Celsius and use an ion catalyst. Okay, so to compromise all these factors, these are the conditions to use. Okay, notice also that the hydrogen and nitrogen are being reused. So by taking away you're basically, by recycling it, you're in pushing the reaction towards the right. So that's an example of the kind of ideas and concepts that chemical engineers need to think about when they're using chemistry to try and increase yields in process. So it's not just about the equilibrium, but it's also about the thermodynamics.